Okay, guys, I want to start this and get this going because we have the final of the several tests that we are doing. Limit comparison is a nice one. There's some tests that I don't like and that you're not going to use that frequently. You do need to know them, but integral test requires very specific conditions. The conditions being that the function is, say it, positive, continuous, decreasing. It needs those three things. This particular one says if the sum from n equals 1 of a sub n is a series we are testing, and it's worth noting that if it's a series we are testing, that means that we know that the sum from n equals 1, or that the limit as n approaches infinity of a sub n has to be equal to what? 0. Because that's what prompts us to test these things. That's a clear distinction I want to make from the last quiz, that if it's not 0, we have no need to test it. It diverges. But if it is 0, if the sequence goes to 0, we're not sure if the series converges or diverges. If the sequence, the limit as n approaches infinity of a sub n, approaches 0 or is equal to 0, we are not sure about convergence or divergence, so we have to launch into this series of tests, pun intended. So if this is a series we are testing, and the sum from n equals 1 to infinity of b sub n is a known convergent or divergent series, then the limit as n approaches infinity of a sub n over b sub n equals L. I'm going to put an if before that. Then if the limit approaches a sub n is equal to L for L between 0 and infinity, then the sum from n equals 1 to infinity of a sub n and the sum from n equals 1 to infinity of b sub n are both convergent or both divergent. It's a comparison, and that comparison is a ratio. This can be used in place of direct comparison many times, and will probably more often than not be used in place of direct comparison because it's just a more encompassing test. So if I'm going to start with this and try an example, the sum from n equals 3 to infinity of 1 over n squared minus 5. Yesterday, we would have tried to do a direct comparison with 1 over n squared. 1 over n squared is a known what? Convergent P series. If it's a known convergent P series, and I tried to compare it, I know that 1 over n squared is going to be, is it greater than or less than n squared minus 5? Less than. It's less than 1 over n squared minus 5, and I know that this is greater than 0, and n squared converges, but that doesn't tell me anything about n squared minus 5. It doesn't trap n squared minus 5. So this direct comparison is out. If you start a test and you don't like where it's going, please don't erase it. Just do some sort of X or line or something so I can very clearly see what work you showed. You can get partial credit for that. It's valuable. It's also good for you to see what you've tried, what doesn't work, and then we're going to move on to this next one. What I am going to do is I'm going to say the limit as n approaches infinity of 1 over n squared minus 5. And instead of doing a direct comparison, I'm going to do a limit comparison where I do a ratio of the two of them. And this is a limit ratio. this is going to be the same as the limit as n approaches infinity of n squared over n squared minus 5, and that limit is 1. 1 is not 0. It is between 1 and negative 1, or between 0 and infinity. So what I can say is, therefore, by limit comparison test, or what I'm going to say is by limit comparison with convergent P series, the sum from n equals 1 to infinity of 1 over n squared, the sum from n equals 1 to infinity of 1 over n squared minus 5 converges. This is the majority of the work you're actually going to end up having to do. It's just writing that sentence out. So it's kind of a sorry, not sorry about that one. Oh, it was n equals 3. You're right. Do you see why it's n equals 3 beyond that point? And that's fine. If you want to start with this with n equals 1 or n equals 3, it's still convergent. Don't get too caught up in the distinctions of that one. Let's do a couple more examples. Actually, we're going to do about 5 more examples. We're going to try to squeeze these in. The sum from n equals 1 to infinity of 1 over n plus 5. If you try direct comparison, or if you just don't feel like doing direct comparison, which is fine now, given the directions that I was going to say, you still need to know how to do direct comparison, but there's no need to with this, because you know that 1 over n plus 5 is going to be very similar to 1 over n. So the limit as n approaches infinity of 1 over n plus 5 over 1 over n. I'm not even going to make you guys rewrite that anymore. You know what that limit should be. 1. That's 1. And then you can just steal the sentence above. Therefore, by limit comparison, I'm going to breathe like crazy. Not that bad, like crazy. With divergent P series, the sum from n equals 1 to infinity of 1 over n. Or you can say divergent harmonic series. The sum from n equals 1 to infinity of 1 over n plus 5 diverges. So the condition that's required is that you do a limit comparison and it ends up being a number. What that essentially means when you do a limit comparison is that one is a direct multiple of the other. That's all you're getting at. By doing a limit comparison, if it establishes that that limit is equal to a constant, then one function is precisely pretty much a multiple of the other, some multiple. And if it's a multiple, you can pull that multiple out and just say it does the same thing. So it's a little bit more of an intuitive type feel to this. Let's do another one. The sum from n equals 1 to infinity of 1 over 3n squared minus 4n plus 5. Do you feel that that one converges or diverges? You should have a feel for these. I would feel the same way. It's essentially the same as what? What would be the one that I want to compare it to? 1 over n squared. So if I do the limit as n approaches infinity of 3n squared minus 4n plus 5 over 1 over n squared, you need to establish what that comparison gets you. One-third. If you're not sure, or if you feel like you're going to mess it up, take the extra step to just rewrite it as n squared over 3n squared minus 4n plus 5. We spent a lot of time in multiple classes talking about ratio of leading coefficients. This is 1/3. So then you say, by limit comparison, with convergent P series, the sum from n equals 1 to infinity of 1 over n squared, comma, the sum from n equals 1 to infinity of 1 over 3n squared minus 4n plus 5 converges. Three more. We're going to make it. Okay, 1 over root 3n minus 2. Compare that one to yeah, 1 over n to the 1/2. So 1 over root 3n minus 2 over 1 over root n. When you do that limit, I'm counting that you guys don't need to show every single step of this limit to understand that the minus 2 doesn't matter, and the ratio becomes the ratio of the leading coefficients, which is 1 and root 3. So your limit comparison gives you 1 over root 3, and all that's important is that that's between 0 and infinity, and it is constant. So that's done. Therefore, by limit comparison with, is it compared to a divergent or a convergent P series? Divergent. Please be very, very, very clear on that. It's easy to mess that one up. The bigger the denominator, the more it would converge. So between 0 and 1 for P series, that's the divergent one. With divergent P series, the sum from n equals 1 to infinity of 1 over root n. We know that the sum from n equals 1 to infinity of 1 over root 3n minus 2 diverges. Two more. The sum from n equals 1 to infinity of n squared minus 10 over 4n to the 5th plus n cubed. N squared minus 10 over 4n to the 5th minus n cubed. This is our first example where it's not immediately obvious what we can compare it to. But what do you think you can compare it to? What is this essentially acting as? Yeah, it is acting as 1 over n cubed. The denominator degree difference is 3 more than the numerator. It is acting like 1/4 times that. You guys see that? At least in terms of limits. Remember, your biggest powers overrule what's going on. So this is acting like a 1 over n cubed type function or series. So what I can do is go limit as n approaches infinity of n squared minus 10 over 4n to the 5th plus n cubed over 1 over n cubed. And I'm going to write this out a little bit more and distribute and kind of simplify this down a little bit. This is truly now the limit as n approaches infinity of n to the 5th minus 10n cubed over 4n to the 5th plus n cubed. And now that you have the degree of the numerator the same as denominator, that limit is 1/4. Therefore, by limit comparison with convergent P series, the sum from n equals 1 to infinity of 1 over n cubed, we know that the sum from n equals 1 to infinity of n squared minus 10 over 4n cubed, or sorry, 4n to the 5th plus n cubed converges. Two more. Kidding. Last one. The sum from n equals 1 to infinity of n 2 to the n over 4n cubed plus 1. What do we know about this? What can we compare this to? Let's start with at least what I can look at with the denominator. What do I know for sure I can kind of do? 1 over n squared, because I got an n in the numerator, n cubed in the denominator. So if I compare to 1 over n squared, now what about the 2 to the n? Yeah, let's do the 2 to the n. And so what do I know about this series? What can I demonstrate about that series? Is it converge or diverge? Diverges. It diverges. Why does 2 to the n over n squared diverge? And so the test that we have is actually the very first test that we ever learned. I know that this diverges because it passes or it fails a very, very, very simplistic version of what's happening whenever I do this, the nth term test. Remember, in order to use these tests, the nth term has to become 0. The nth term test for this one says that the limit as n approaches infinity of 2 to the n over n squared equals what? Infinity. It equals infinity, and I want to spend just a second on this. I'm going to change this color because this is sort of a little separate thing. I want to spend a second on that. You know that this is infinity. Your intuitive reason is that the numerator explodes faster than the denominator. The proof reason uses what? L'Hopital's. Yes, this is a L'Hopital's. This is infinity over infinity. And I want to just spend a second on this because we need to establish conclusively that that diverges. So the first is to establish that we use the comparison. The second is to say I intuitively know that this diverges because the nth term test right here is what we're going to use. And now I do a derivative, ln of 2 times 2 to the n over 2n, infinity over infinity. And then finally get limit as n approaches infinity of, this would be ln of 2 squared times 2 to the n over 2. That is equal to infinity. That is conclusively equal to infinity. This I wouldn't say is completely necessary, but it is important to know why and where you could prove that you know that it is. Probably the biggest confusion that I sense you guys are going to have has to do with the nth term test and the difference between the nth term of a sequence versus the nth term of a series. So go back, look at that part. Keep this test as kind of clearly defined in your head as you can, because going into the list of convergence divergence tests, you're going to notice right here that the first thing you do in the flow chart is you're doing an nth term test to test for divergence. It is a test for divergence, and if you fail that test, you don't have to do any other test on anything. You know that the thing diverges. So this flow chart is on your binder now. It's a good one to have. It's a good one to see, to get an idea not only of what we've used, but also what's still out there and where we're going with this. So let's go back. We're going to do the limit. Oops, the keyboard's coming up. Let's change this back to blue. We're going to do the limit as n approaches infinity of n times 2 to the n over 4n squared plus 1 over 2 to the n over n squared, 4n squared plus 1. I read it right, I said it wrong, but let's make sure it's right. It's 4n cubed. Okay. That limit is equal to, what do you think it is? It is 1/4. If I bring it all together, which is a good step to do if you're just a little iffy about how this is playing out, I get n cubed times 2 to the n over 2 to the n times 4n cubed plus 1, and my 2 to the n's drop out. And my limit is just 1/4. So finally, by limit comparison, with divergent for reason of nth term test series, the sum from n equals 1 to infinity of 2 to the n over n squared, this series n equals 1 to infinity of n times 2 to the n over 4n cubed plus 1 diverges.